We will. We will. Yeah. Yeah. So I do have some material left to cover. That's what you're asking? Yeah. So this was the handout that I gave you before the quiz. And let me uh, do a very quick recap of what we've been talking about. So we dealt with tensor invariants, two types of invariants, primary and principal. We learned how to solve for these, and I showed you that this particular tensor that we looked at in the example had eigenvalues 3, 4, and 6. And what it did was basically scaled. We also found the eigenvectors n1, n2, n3, and we tried to visualize what this tensor looks like. And we came up with something like this, which has n1 along e1, n2 and n3 along these directions. And this tensor would scale those eigenvectors by 3, 4, and 6, and you would get a big ellipsoid, which is what this tensor can be visualized as. Okay. Then I very quickly went over the common commands in MATLAB that you could use to solve for that. And we were looking at these two special cases as a case of one repeated root, which means that two particular eigen directions, n1 and n2, for example, in this case, would be the eigenvalue would be corresponding to them would be the same, and therefore any vector in that plane, n1, n2 plane, any vector in that plane would be an eigenvector, and it would be scaled by exactly the same amount lambda, which could be lambda 1 or lambda 2. Right? And the special case of all three eigenvalues the same, which just takes a sphere of R. So let me ask here, is this concept of the sphere going to an ellipsoid, is that meaningful? Does that make sense? What do I mean by this red sphere? What is this red sphere? It's all possible unit vectors at that point, right? So centered at that point, if you think of a unit vector, that would be some vector of length 1 pointing in arbitrary directions. So if you take the set of all those possible unit vectors, you would get this ball of red sphere. But actually, what you should think about is something like this. You have one ball of red sphere of unit vectors in all arbitrary directions. Right? But in each direction, there are infinitely many possible vectors as well. Right? You can have some very small vectors, larger vectors up to a unit vector, which is what we have been talking about. And of course, larger vectors than that. So what you're really looking at is, at a point, a bunch of infinitely many possible vectors. What does a tensor do? It takes all of those possible bunch of vectors and it stretches them in n1, n2, n3 by lambda 1, lambda 2, lambda 3, and everything in between by appropriately, and it gives you a full space of vectors. So starting from one space of vectors, that's this, to a new space of vectors, that's the blue ellipsoid corresponding to this. So I'll come back to that. But that's what that visualization of a tensor should be clear in your mind. All right, so spectral decomposition is about where we were last time. We said that for any tensor, I can express a tensor, any symmetric tensor, I can express that tensor in terms of its eigenvalues and eigenvectors. So for example, a tensor T that looks like this, there are three particular directions, at least three particular directions, in which there will be only scaling of that vector. Any other vector in between would likely have a change in magnitude and a little bit of rotation, right? So the spectral decomposition theorem says that if I have a tensor T, I can expand it out as lambda 1 times n1 dyad n1, and for the 2 and 3 components as well. And if you write that in indicial notation, you get this, where there are three i's floating around, so we do have to have that sum. And we looked at the example from the last example. We took this tensor, we expanded it in terms of its own eigenvectors, 3 times N1, 4 times N2 diode N2, 6 times N3 diode N3. And of course, if you sum all of that up, you get back to the original tensor T. So this works for any symmetric tensor. Okay, it's a useful decomposition theorem, as you'll see later on when we are trying to figure out principal stresses, principal strains. This theorem will come in handy. All right. Another property of this spectral, or another useful way to think about this spectral decomposition is this, that if you have a tensor T, this tensor, and some arbitrary vector U, I can express that tensor T in its spectral decomposition form and have that tensor act on U just like here. What would be the result of that? How can we figure out what would be the result of that? Yeah, we'll come to that. But here, tensor T acting on U, we have this as the spectral decomposition of the tensor. And acting on U, we just use the property of the dyadic product that these two vectors will get dotted, right? So that would give me sum of I going from 1 to 3, lambda I U, sorry, not UI, but the vector U dot with Ni, and in the direction Ni. And the reason that this is interesting is because U dot with Ni, what is that? Component of U in the Ni direction, right? So I just said here that if I have this tensor that takes this arbitrary vectors to this blue ellipsoid, there are these three directions. If I express the tensor in these three directions, and even the vector in these three directions, then I can take any arbitrary vector here, find its components in N1, N2, N3. And what this tensor then does is that it takes that component in the N1 direction, scales it by lambda 1, takes the component in the N2 direction, scales it by lambda 2, takes the component in N3, scales it by lambda 3, and just this gives me three perpendicular vectors to each other, right? And then you multiply those, or you do a scalar multiplication of those with their corresponding eigenvectors, and add them together to get the result. So I will write that as UI in the basis N1, N2, N3. Right? It's not U1, U2, U3 in E1, E2, E3 basis. It is U1, U1 prime if you want to think about it in the N1, N2, N3 basis. So if you want to figure out what a tensor does to a vector, one way to think about that is to take the vector that you are considering, find its components in the N1, N2, N3 basis, which are the eigenvector basis, and then just scale them by lambda 1, lambda 2, lambda 3 and add them. That's what a tensor would do to a vector, to an arbitrary vector.
And the two vectors that are in the N1 and the N2 direction should have the same magnitude.
No, this is not about a special case. This is for any arbitrary tensor. Yeah, this is for any arbitrary tensor, any arbitrary vector, not arbitrary tensor, but symmetric arbitrary tensor. So, right. And here's another way that the spectral decomposition is useful. Let me ask you this. If I go back here, we had this tensor. This tensor was in the E1, E2, E3 basis, right? We found eigenvectors. So this, for example, here was N1. Same thing here. Both of these were N1. This divided by square root 2 was N2. Same thing here. This divided by square root 2 was N3. Now, N2, for example, is written as 1 over square root 2, 0, 1, 1 in the E1, E2, E3 coordinate system. Can you tell me what it is written as in the n1, n2, n3 coordinate system? What would be n2 in the n1, n2, n3 coordinate system? 0, 1, 0, right? It's 0, 1, 0. So similarly, n1 in the n1 coordinate, n1, n2, n3 coordinate system would be 1, 0, 0. Even though n1 or n2, n3 have different components in the even e2, e3 coordinate system, they would just be simple 1, 0, 0, 0, 1, 0, and 0, 0, 1 in these three coordinate systems. Therefore, another way to write the same tensor T would be using the spectral decomposition theorem would be lambda 1, n1 dyad n1 plus lambda 2, n2 dyad n2 plus lambda 3 n3 dyad n3. So if I do that for this particular tensor, I can write that as 3 times n1, which would be 1, 0, 0, 1, 0, 0, plus 4 times n2, which would be 0, 1, 0, 0, 1, 0, and plus 6 times n3, which would be 0, 0, 1, 0, 0, 1, and all of this is with respect to the n1, n2, n3 coordinate system, which means that the same tensor T in the n1, n2, n3 coordinate system would be just 3, 4, 6 on the diagonals. Okay, and this would be true for any symmetric tensor. Basically, you have any tensor in the even e2, e3 components, find its eigenvectors, and in the direction or in the coordinate system of its eigenvectors, the eigenvalues would be on the diagonals. Everything else would be 0. Okay, so the same thing holds for any arbitrary tensor. That's why I was going to write this here as lambda 1, lambda 2, lambda 3 in the n1, n2, n3 coordinate system. Okay, so you could be given a tensor in some coordinate system, even e2, e3. You find its eigenvalues and eigenvectors, and in that particular basis, n1, n2, n3 basis, your tensor would be diagonal. Okay, that's a very useful theorem. All right. Now, we've talked a little bit about what the invariants mean physically, but there's a very nice interpretation for the physical meaning of these principal invariants. Okay, so let me ask you to consider this. By the way, this basis, a tensor expressed in its own n1, n2, n3 basis, which is called the canonical basis. Okay, so let me ask you to consider this sort of a picture here. I just told you that that in general, at a point, we don't have just a ball of arbitrary unit spheres, unit vectors. You really have infinitely many balls of arbitrary vectors all together, right? What I'm asking you to do now is to consider 3 particular vectors out of this ball of arbitrary vectors. Which 3 vectors? I'm going to ask you to consider a unit vector along n1, a unit vector along n2, a unit vector along n3. Okay, so the sides, if you put all of these 3 vectors as the sides of a cube, all of these sides would measure 1, and their directions are along these eigendirections. Okay, so let me ask you this: when the tensor T acts on this unit vector along n1, what does it produce? Sorry? n1 lambda 1. So the direction n1 remains the same, but the vector gets scaled by lambda 1, right? So what I'll do is that I'll say that this guy along n1 goes to this blue vector, which I'll call the side length would be lambda 1. The direction would still be n1. Similarly, the direction for n2 and n3 would still remain the same, but the side, the length of the side here would be scaled by lambda 2 and lambda 3. So each one of those sides of the cubes gets scaled by lambda 1, lambda 2, lambda 3. Right? So if you were to plot the shape of the new cube, it would be some sort of a cuboid. Will the angles be 90 degrees after the action of the tensors? Yes, because n1, n2, n3 are orthogonal to each other, right? And when the tensor acts on n1, n2, n3, these particular vectors' directions do not change. So if it's 90 degrees before, it will be 90 degrees after. Right? For any other vector, if it's not an eigenvector, the direction would also change a little bit, right? All right, so what's the usefulness of this? Let's take a look at the first principal invariant, which is also the first primary invariant, which is basically lambda 1 plus lambda 2 plus lambda 3. Why? Because that's the sum of the diagonals, correct? That's the first principal invariant. Sum of the diagonals will always be lambda 1 plus lambda 2 plus lambda 3, no matter what coordinate system you choose, because it's an invariant, right? Can you tell me what physically it means, lambda 1 plus lambda 2 plus lambda 3? Sum of the modified lengths, right? So each side got scaled by lambda 1, lambda 2, and lambda 3. So if you were to go along n1 direction in lambda 1, go along n2 direction by amount lambda 2, go in the n3 direction by lambda 3, you would go from one corner of the cuboid to the other corner of the cuboid. So it's kind of, the first invariant is proportional to change in length. Change in length of this cube to cuboid. How about the second invariant? Second invariant, you can actually calculate and convince yourself that the second principal invariant was here. This was the second principal invariant, correct? For you can check this and you can verify that this would be equal to lambda 1 times lambda 2 plus lambda 2 times lambda 3, lambda 3 times lambda 1. Can you tell me what is lambda 1 times lambda 2? Area of the face n1, n2. So initially I started off with an area of what? 1, right? 1 times 1 is 1. And the final area in the quote-unquote deformed in the deformed system, or after the tensor has acted on it, the deformed area would be lambda 1 times lambda 2 of that face. Similarly, you have lambda 2, lambda 3 would be the area of lambda 2, n1, n2, n3 face, and all of those. So second invariant is proportional to changes in area, right? And finally, what is lambda 1, lambda 2, lambda 3? Product of all of that? Volume of the cuboid. So third invariant is proportional to change in volume of the cuboid. Okay, so this is a sort of a useful way to remember or to understand the physical significance of these invariants. Questions? All right. Another interesting property. Go ahead, Nikita.
When you say lambda 2 is proportional to change in area, or lambda, invariant 2 or invariant 3 is proportional to change in area or volume. Can't we just say that they are proportional to the volume or the area, because anyways it's going to be constant?
No, because what we assumed was that the original length of the sides of the cube were 1. So the invariant itself is associated with a tensor, right? A tensor, all that it does, it takes infinitely many arbitrary vectors in one space, modifies them to infinitely the correspondingly mapped vectors to another. So there's no volume here as such, right? Tensor itself is not associated with some volume. But when tensor acts on a set of unit vectors, these red unit vectors, it takes them to these blue corresponding map vectors, which will not be in general a unit vector. The change in volume in going from this red space of vectors to this blue space of vectors, that's what the third invariant captures. So actually what we'll also look at in the next chapter would be something called deformation tensor. Deformation tensor, the third invariant is actually equal to changes in volume. So you have to define an initial body, right? Initial body is this cube of unit dimensions. So the volume of this cube is 1. If this volume is not 1, then it's only the change in volume that you can define, not the actual absolute volume, if that's what you're asking. All right, so if you have more questions, we can definitely talk about that in our office hours. But okay, there's this interesting theorem by Cayley-Hamilton, which says that given a tensor, if you plug that tensor into its own characteristic equation, hopefully you recognize that this is the characteristic equation of the tensor T, except instead of lambda cube, I have T cube here, T components acting on itself. Instead of lambda square, I have T squared. Lambda is replaced by T, and I cannot have just the third invariant sitting here. It has to be a tensor, and the right hand side also has to be a 0 tensor. So if you compare this to the characteristic equation, I've tried to stay consistent with having tensors on both sides. And yes, the interesting thing is that a tensor satisfies its own characteristic equation. And this can be proved, but this is comes in handy in a lot of other proofs also. Something interesting to just note and keep in mind. Okay. So I'm not giving you a proof and all that. I'm sure you can look up other sources if you want to explore that. All right, so we'll change gears here a little bit and talk about calculus of scalars, vectors, and tensors. We've been talking about, first of all, what these things are. We've talked what these tensors are, something that acts on a bunch of vectors to give me another bunch of vectors. That's what a tensor is. But we usually don't work with just one scalar or tensor or vector quantity. We work with fields of these quantities, right? What does that possibly mean? If I have a structure, some solid body, then it has infinitely many points in it, and what we're looking at is how a particular field changes from one point to another in this volume. For example, if I were looking at temperature, maybe the bottom is cold, the top is hot, then I'd want to know what is the rate of change of temperature from bottom to top. Okay? Because the rate of change of temperature is what will define or what will govern how fast heat flows from the hot to the cold surface. Right? In the same way, if I'm looking at say deformations, then when the structure deforms, what I want to know is that how quickly is the deformation changing? Meaning that if I have 2 points that are close to each other in the initial undeformed configuration, then how far apart are they in the deformed configuration? And how does that deformation change from point to point? Maybe I have regions like, let's say something like this, like a cantilever beam with a tip load, right? Now, in which regions of the cantilever beam is the deformation the highest? The tip or the attached or the fixed support? Why is that? The thing about bending moments, at which points in the beam are the bending moments the highest? A fixed point, right? Bending moment for a cantilever with a tip load, of course, is a triangular shape. So the bending moments are highest here, which means that if you look at the top surface, it has lots of tension. The bottom surface has a lot of compression in it. And if you look at the bending moments here, very small. So even though the absolute displacement of the tip, is much greater, the relative displacements between points is not as big at the tip, right? Because the bending moments are small, the amount of tension and compression in the bottom and the top fibers is not as much. So if 2 points were close before, they probably became slightly closer or slightly more farther apart, but not as much as points near the stick support. 2 points here got much more in tension, so they got much more farther apart. 2 points here got much more in compression, so they got closer together. So we always have to sort of work with these quantities, scalars, vectors, and tensors as fields. What is its value at one point? How is it changing from point to point? And to do all of that, you have to rely on calculus. That's what calculus does, right? It measures the rate of changes of things, allows you to do integration of fields and so on. So that's what we are going to look at. Let me start with the simplest possible case. A scalar field of one variable. What does that look like? It looks like some function fx. I have a scalar field f of one variable x. So instead of a three-dimensional space, x, y, z, I have only x. And a scalar function of that would be something like f of x. We obviously know that derivative, or we can measure the rate of change of that function using the derivative. And hopefully you all remember that the derivative is defined in this way, that you take the function value, if you want the derivative at point x, take the function value x plus delta x, subtract it from fx, and divide it by its length, right? And take the limit delta x tending to 0. That's how we used to define derivatives. But this definition of a derivative does not generalize very well to these other quantities that we are going to talk about, vectors and tensors, especially in 2D and 3D. Okay, so I'll write a definition of a derivative that will be exactly this, not exactly, but it will be very similar to the definition of corresponding derivatives of scalars and of vectors and tensors in 2D and 3D. So one way to look at the derivative is that it is the flux of f on the boundary of ran a space here, on the boundary of delta x. What do I mean by that? Flux of f on the boundary of delta x, and I'm going to take all of that and divide it by a measure, I'll say a measure of delta x. So when I say flux, what it means is that if I consider some delta x elemental length, in this case elemental area or volume, we will take the value of, we'll consider this as a small infinitesimal body. Right? We will consider this delta x as a small infinitesimal body. It has two boundaries, one at x plus delta x and one at x minus delta x. The unit normal of a body is the outward pointing unit vector at this point and at this point. So at this point, the outward pointing unit vector is just pointing along the x direction. So if I were to represent that in coordinates, what would it be? I should not write it equal to, can be represented with 1, 0, 0, yes, if it were a three-dimensional space. But here we are just talking about a one-dimensional space, right? So we would just represent that with 1. Here, similarly, n at the negative end, or n minus is pointing in the negative x direction. So that would be represented with -1. The unit vectors in one-dimensional space can just be +1 and -1, right? So the flux is defined as the value of f at one boundary of the body times the unit normal n plus f at the other boundary times the unit normal n minus, and divided by the measure of the body, which in this case happens to be the length of that delta x. And what we have is exactly that same definition that we had up there, but expressed in terms of a flux. And the usefulness of this concept of understanding the flux of a quantity will be clear when we deal with scalars and tensors in 2D and 3D. Okay. All right. Since I don't have too much time here, I'll just talk about this other important theorem that you've learned, something called the fundamental theorem of calculus. Right? Really important fundamental theorem of calculus. What it simply says is that if I have a function f, a continuous function f, that looks something like this, and actually I'm plotting here the derivative of that function. So for example, if I have some function here, and if I plot the derivative of that function, it could be something like this. What this theorem simply says is that if you take the integral of this derivative between 2 points A and B, it would be simply equal to the values fb minus fa, which you all learned in basic calculus, right? But again, for vectors and tensors in 2D and 3D, there are corresponding different ways of thinking about these integral theorems. But these are the two things that we'll try to generalize in the next lecture for vectors and tensors: derivative operations and integral operations. All right, so let's stop here and we'll continue on Friday.